Okay, let's take a look. We got 24 electrons, and then put the carbon in the center, 3 oxygens. Then what did you do? Is you complete the octets to all the atoms by using lone pairs. First 3 oxygens because they're more electronegative than the carbon. Then you count how many electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. The 26 electrons there, 24 electrons here, so we run into the exact same problem. We have 2 electrons too many. And so we're going to remove them from which atom? From carbon. If we take them off carbon, then that gives us 24 electrons, but now carbon doesn't have an octet. And so what oxygen has to do is it has to contribute a lone pair into a bonding pair, and then we can make an octet. So we have 3 oxygens. Which one should we pick, or does it matter? It doesn't matter. It doesn't matter because they're all the same. But it does matter because we have 3 choices. And so those 3 choices are going to give us 3 different looking structures. What we're going to do is we're going to leave the atoms in place. So if we pick this one, let's say, and make a double bond here, we'll call that option 1. Okay, now everybody has an octet, and so everybody should be happy here. And so that looks good. Everybody has an octet. And so what we want to do is formal charge. This one's 0, this one's -1, this one's -1, and this one's 0. So we aren't going to write the non-zero. And then we sum up the formal charges. The sum of the formal charges will be the net charge. So -1 plus a -1 gives us 2 minus. That's if we pick the left oxygen, but we have 3 unique choices for the oxygens. We could also pick the top oxygen instead. And so instead of picking this one, let's say we pick this one, we'll call that choice 2. And so in this case, I'm going to form the double bond up like that. This. So this will be negative, this will be negative, and we'll get a 2 minus. These are called resonance forms. You see pretty much the same structure, we just had a different way of arranging the electrons. We keep the atoms fixed in position. And so I don't want to start rotating it or moving it. The atoms are going to be pinned to the page. If I pin the atoms on the page, then I can see the 2 different ways of arranging the electrons. In fact, there are more than 2 different ways of arranging electrons. There's actually a 3rd way. So if I do it like this, 3rd way, I'll draw it down here. That is, make the double bond to the right. So I get a negative formal charge here, negative formal charge, and lose atoms to 2 minus. Okay, so it turns out that there are actually 3 resonance forms, and all these resonance forms for this will be equal in terms of energy. You know, one resonance form doesn't look worse. Like in the previous example, for bicarbonate, one of the resonance forms didn't look so good because of the result of having one oxygen positive and the other oxygen negative, which means that one oxygen lost, the other oxygen gained. And so 3 resonance forms for this. So we'll get some more practice with Lewis structures. Lewis structure is an important skill to have in chemistry. All right, so let's take a look at some of the homework problems from the book. And, the first one is draw Lewis diagrams or Lewis structures for each of the following sets of molecules HI. for something like HI, I might just do it based on this. Just draw the Lewis symbols. These are called Lewis symbols. And realize iodine wants what? Iodine just needs one more electron, and then it's got an octet. It's filled its valence shell. Hydrogen needs one electron to fill its duet first shell. And so hydrogen is going to try to take that electron. Iodine is going to try to take the electron. Iodine's stronger, more electronegative, I think. And so it's going to try to pluck that electron. Well, hydrogen is strong, though. It's not going to let it go. So what we're going to have is a scenario where it's not ionic. It's going to be covalent. There's going to be sharing, but it's going to be unequal sharing because they don't have equal strength. So it would be something like this. Try. Oxygen, on the other hand, wants 2 electrons to complete. And it's going to get it from hydrogen, or try to get it from hydrogen. So oxygen will try to strip the electrons off hydrogen, but it's not strong enough to completely strip them off. So sharing is going to result. Again, unequal sharing. This is going to be a polar covalent bond. Finally, nitrogen. Nitrogen wants 3 electrons to complete its octet. So from chlorine, it could get 1 because chlorine has 7 valence electrons, just 1 unpaired. And chlorine wants 1 more electron as well. So we'll try to take it from nitrogen. Well, it's not going to be able to completely pull it off. Either way, chlorine or nitrogen. So it ends up sharing. Yes. Let's take a look at the electronegativities again to see what type of bond that is. So nitrogen, chlorine, ooh, nitrogen is 3.0, chlorine is 3.2. So the nitrogen-chlorine bond we would consider pretty much a tie. They're so close, it's a tie. And so we call it a non-polar bond. Hydrogen-oxygen bonds are quite polar. And the hydrogen-iodine bond, I'd expect that to be polar as well, but I'm not sure about iodine. Let's see what iodine is. Iodine's at 2.7, hydrogen's at 2.2, so the difference is 0.5. 0.5, that's borderline non-polar. That's the situation we have. But we're concentrating on Lewis structures right now. We'll look at the polarities more later. So these are the 3 Lewis structures, HI, H2O. Now, they drew their H2O differently than I did. You see, their H2O has a kink, a 90-degree angle here. Mine is like 180. You see that? But for Lewis structures, there's something you got to realize. Lewis structures don't have to be accurate. Lewis structures are just trying to show the connections. And so none of these are accurate. In fact, when I look at this looks like 90, but it's not. This looks like 90, but it's not. This is pretty accurate because there's only 2 atoms. And so it doesn't matter how I drew it. Like, for example, I drew mine 180. It doesn't matter. If they drew theirs 90, mine's not correct, theirs is not correct. Lewis structures, we don't really care about being accurate with the shape of it yet. I'll talk about the shapes of these later. But right now, we're just looking at the connectivity, how things are bonded together. Let's take a look at HF, OH2, and NF3. HF, I would just do HF like this. Hydrogen has 1, fluorine has 7. They both want 1 more electron. Is this going to come out ionic? I don't think so. Because when we look at the electronegativity chart, hydrogen is a 2,2, fluorine is a 4,0. That comes out 1.8. Oh, that's borderline ionic. I told you the cutoff is like 1.5. Borderline. It's not so clear cut though. Turns out this is more polar covalent. So the molecule that results is like this. You know, it's it's quite close to being ionic. Maybe I should bump it up to 2. You know, delta En of 2 and greater to be ionic. So these are still 2 nonmetals. You know, nonmetals typically form covalent type bonds. OF2. Oxygen wants to form 2 bonds. Fluorine wants to form 1. The fluorine's going to try to strip the electron off oxygen, but it's not going to be successful at stripping the electron because it's delta En, oxygen, fluorine. Let's take a look. Oxygen's a 3,4, fluorine's a 4,0. So it's a 0.6. So they're going to share. So it's going to look something like this. Everybody has an octet. Are there any formal charges? No formal charges here. Are there any formal charges here? No formal charges there. The other thing we look at is what? Oxidation state. The oxidation state is more for redox properties than for Lewis structures. And so let's go on to the next one, NF3. NF3, nitrogen likes to form 3 bonds, fluorine likes to form 1 bond only. So it's going to look like this. That would be the Lewis structure for NF3. If I look at the formal charges, all the formal charges are 0. But would you consider NF3 electron rich like ammonia? You know, if you look at ammonia, you know, nitrogen has an octet, this nitrogen has an octet. And so ammonia and NF3 are kind of similar in that sense. Would you expect nitrogen to be electron rich in NF3? You know, over here, nitrogen is electron rich. So it's -3 oxidation state. In NF3, is nitrogen as electron rich? No. In fact, in NF3, it's the opposite. What is the oxidation state of nitrogen in NF3? It's winner take all. So nitrogen versus fluorine, who's more electronegative? Fluorine. So fluorine takes all of them. Nitrogen versus hydrogen, who's more electronegative? Nitrogen versus hydrogen, which one's more electronegative? Nitrogen. Nitrogen versus fluorine, fluorine. This is kind of the opposite situation here. In this particular case, nitrogen gains all the electrons, so it ends up with 8 electrons. It's supposed to have 5, so it gets a -3 oxidation state. Over here, the opposite situation happens. Fluorine takes all the electrons. And that leaves nitrogen with only 2. Nitrogen's supposed to have how many? 5. So if it's supposed to have 5 and only has 2, it's a deficit of 3 electrons. So it's going to be +3. And so do you see, on the one hand, this nitrogen here would be considered electron rich. This nitrogen would be considered electron poor. And so the redox behavior of these two are quite a bit different. quite a bit different. But both of them have octets. Both of them have zero formal charge. And so by looking at the oxidation states, we can get an idea about the redox properties. All right, when we get to the number 3, I'm going to stop doing them like this. We're going to start using the steps, like for CO2. It's probably easier to go through the steps. And this one. Sometimes it's easier to do the steps, sometimes it's easier just to visualize what's happening. And so carbon's got 4 electrons, 2 oxygens would be 2 times 6 electrons, which would be 12. 12 and 4, 16 electrons altogether. And then we make a skeleton with carbon in the center with 2 oxygens, and then complete the octet to oxygen first, and then to carbon. And then how many electrons have we used up? Well, it looks like 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. It structure has 20 electrons. I only have 16, so I have 4 electrons, too many. And so I have to remove some electrons. Who should I remove the electrons from? Carbon or oxygen? Carbon. And so what I'm going to have to do is I'm going to have to take 4 away. Well, that means carbon's very far from having an octet. And so what I'm going to do is I'm going to make a double bond. Like that. If I make 1 double bond, is that enough? No, it's not enough. You see that? Carbon still doesn't have an octet. So what should I do here? I have a choice. I can make a triple bond. Should I make a triple bond? Then carbon would have an octet. No, I shouldn't make a triple bond. Instead, I should make another double bond. And that would be a more equitable situation. So what I'll just do is make another double bond. And so now everybody has an octet. Oxygen has an octet, carbon has an octet, oxygen has an octet. So the octet is good. Are the formal charges? Are there any formal charges on this? The goal is 1, octet. That's the main goal. The second goal is to minimize the formal charge. It's best if there are no formal charges. And if there is a formal charge, try to minimize it. Are there any formal charges in this structure? No. So formal charges are good. So this looks like a good structure here. SF2 is next. Sulfur has 6 electrons, 2 fluorines, 2 times 7 electrons each. That's 14 plus 6 is 20 electrons. And then we place the least electronegative, which would be sulfur, most electronegative fluorines on the outside. And then we complete the octets to fluorines first, and then sulfur. And then we count the electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. 20 electrons, so they matches, right? I'm supposed to have 20 electrons. Now look, does everything have an octet? Yes. Fluorine has an octet, sulfur has an octet, fluorine has an octet. What about the formal charges? Are there any formal charges? Formal charges, well, fluorine has 2, 4, 6, 7. It's supposed to have 7, 0. Sulfur is supposed to have 6. How many does it have? 2, 4, 5, 6. It has 6. This sulfur has 7. All the formal charges are 0. And so this is a good structure for SF2. And then BrO3 minus. Sulfur difluoride, BrO3 minus is called what? Bromate. And so let's take a look at bromate. Ooh, we don't have time. We'll take a look at bromate tomorrow. We're out of time today. So stop here.